multiple roots. There is an easier way of finding multiple roots other than continually using the factor theorem again and again and again. It's a lovely little result. If a function has a multiple root, let's say its multiplicity is m, then the derivative will have that same root, but its multiplicity will be one less. So if a function's got a double root at a particular point, then its derivative will have a single root at that same point. When you think about it, that makes sense, because a double root is like a turning point. So it would be a stationary point. So when you differentiate it, the derivative would be 0 as well. That's basically where it comes from. But a better proof is something like this. So our polynomial is going to be written as x minus a to the power of m, there's the multiple root, times some other polynomial. And of course, in that other polynomial, x equals a can't be a root, because otherwise the root would no longer be of multiplicity m. It would have more multiplicity, if that's such a word. Differentiate it, I'm going to have to use the product rule. So write down the first, diff the second, well, we'll just call that q dash x, whatever that happens to be. Write down the second, differentiate the first bit, got to use the chain rule, bring down the power, lower the power, diff the inside, but you'll see that the two algebraic expressions I have a common factor of x minus a. In fact, x minus a to the power of m minus 1. Now, inside the square brackets there, I'm not really concerned with what that actually is. What I do know is a is not a solution to what's in the square brackets, because we said it's not a solution of qx, so therefore when I sub in, it won't all be 0. And the power has been reduced by 1. So I could write that as x minus a to the power of m minus 1 times some polynomial. So there's our theorem, which can save us some time if we are aware of multiple roots existing. So here's an equation to solve, but they've told us it's got a double root. So rather than trying to solve the cubic, what I'll do is I'll differentiate it and try and solve the quadratic, because a quadratic's easier to solve than a cubic. So 3x squared minus 8x minus 3 factorises to be 3x plus 1, x minus 3. So I have two possibilities for the double root. It's not to say that they both will be, but one definitely will be. Which one of those two would you logically check? Look at the original equation. Look at the two possible factors. Which one would you logically think is the double root? Anyone? Why? Oh, and you're right, x minus 3 is the logical choice. Question is, why? If 3x plus 1 was the double root, then when I factorised x cubed minus 4x squared minus 3x plus 18, what would be a factor if 3x plus 1 is a double root? Wouldn't 3x plus 1 squared be a factor?
Yes.
Okay, thanks for that. Now when you expand out 3x plus 1 squared, how am I going to end up with this monic? X cubed minus 4x squared minus 3x plus 18. Wouldn't it be more logical to test the x minus 3? Because 3x plus 1, in order for that to be a factor, we would have to do a lot of manipulation. X minus 3, 3 goes into 18, 1 goes into 1. That fits nicely. 3x plus 1, 1 goes in 18, 3 doesn't go into 1 evenly. Remember we said when we were testing for roots, if it's going to be a fractional answer, the top of the fraction goes into the constant, the bottom of the fraction goes into the leading coefficient. It's monic, so therefore it's logical that the factor, if it's monic, is just going to be x, not 3x. All right, let's test, see if we got it right. What I'm getting at is I'm going to test 3 first. So it's going to be minus a third or 3. I say that's not going to be possible because 3x plus 1 is not a factor of my polynomial. But let's test. When you I didn't actually write it down. I should have written it down. That was bad. Polynomial 3, when you substitute it in, does become 0. So it works out. So when I factorise it, I now know x minus 3 squared is a factor. And the other factor then turns out to be x plus 2. Let's go solve it. There we go. X minus 2, x is 3. Let's try something more interesting. Really nice question. It comes from 1991, which of course is a palindrome. I know that's the first thing I see when I look at 1991. But look at the actual polynomial itself, the coefficients. 1a, b, a1. Also palindromic. How cool is that? Where 2 plus b squared does not equal 4a squared. Well, you probably realised that. Maybe not. All right, we have to show that the root can't be alpha. Well, it can't be alpha. It is alpha. Can't be 0, 1, or negative 1. So clearly 0 is not a solution. Sub it in, you get 1. Doesn't satisfy. Sub in 1, we get 2a plus b plus 2. At this stage, I can't be sure that that's not 0. So let's sub in negative 1. Let's see what happens. I get minus 2a plus b plus 2. That's interesting. Very similar. That's where this piece of information comes in handy. 2 plus b squared can't equal 4a squared. So therefore, 2a plus b can't equal plus or minus 2a. Well, that means plus or minus 2a plus b plus 2 can't equal 0. So now we go back to what we got when we substituted in 1 and minus 1. We know they can't equal 0. So therefore, polynomial 1, polynomial minus 1 can't equal 0. Hence, alpha can't be plus or minus 1. So in that particular question, showing the 0, I guess, was the gift mark. The 1 and the minus 1 was the tricky bit, tying in the other piece of information we'd been given. All right, we're now going to show that 1 on alpha is also a root. So if I substitute in 1 on alpha, in order for it to be a root, of course, I need to get the answer 0. Algebraic fraction, we'll put alpha to the power of 4 on the bottom of the fraction. The top becomes 1 plus a alpha plus b alpha squared plus... But hang on a sec, we know alpha's a root. So the top of that fraction is equal to 0. Because it's polynomial alpha, and we've already determined polynomial alpha is equal to 0 if it's a root. So, all right, we now know that 1 on alpha is a root if alpha is a root. So in other words, if 2 is a solution, so is a half. If 3 is a solution, so is a third, and so on and so on. So we're going to deduce that if alpha is a multiple root, its multiplicity has to be 2. Got to be a double root, can't be any more than that. And also, much more interestingly, 4b is equal to 8 plus a squared. Here's my logic. If alpha is a double root, then so is 1 on alpha. Because we just proved that whenever alpha is a root, so is 1 on alpha. So if alpha appears twice in my solutions, so does 1 on alpha. So that gives me 4 solutions. But the polynomial was a quartic. And we know a quartic has a maximum of 4 solutions. So there are no more solutions. They are the 4 solutions. Alpha, alpha, 1 on alpha, and 1 on alpha. So no more roots, so they can't be more than a double root. Because if they are anything more, I'd have more than 4 solutions to this quartic, which I can't have. All right, now I'm going to prove this 4b part. So let's find the derivative. We know if it's a solution to the polynomial, it's a solution to the derivative as well. And there's our derivative. I'm going to say the roots of this. I know alpha is a solution because it was one of the double roots. I know 1 on alpha is a solution to the derivative because it was one of the double roots. There will be a third solution, don't know what it is. Let's just call it beta. Sum of the roots, alpha plus 1 and alpha plus beta, will be minus 3/4 a. Sum of the roots 2 at a time. 1 plus alpha beta plus beta on alpha is a half b. And the product of all the roots, well, the 1 on alpha times the alpha becomes 1. So I now know that beta, that third root, is minus 1/4 a. All right, let's play around with that. If I substitute the third one into the first one, I get alpha plus 1 on alpha is minus 1/2 a. If I substitute the third one into the second one, eventually we get our result. Right? So you'll notice I was able to factorise the alpha plus 1 on alpha, which we've just said is equal to minus 1/2 a. So I've substituted that in, got rid of the fraction, and there's my result. Coincidentally, exercise 5b in both of them. Ooh, isn't that nice?